Space is a hostile place. Beyond Earth's protective magnetic field, radiation becomes a silent, invisible threat. And on Mars, this danger is amplified. With a thin atmosphere and no global magnetic shield, Mars is bombarded by cosmic rays and solar energetic particles on a daily basis. Radiation exposure is one of the most critical challenges for long-term human survival on the Red Planet. On Earth, we're protected by the magnetosphere and a dense atmosphere that shields us from harmful solar and galactic radiation. Mars offers none of those safeguards. According to NASA, astronauts on Mars would receive radiation doses just over the agency's acceptable career limit for deep space missions. Without proper shielding, this exposure could lead to a significantly higher risk of cancer, nervous system damage, and even acute radiation sickness. So how do we protect ourselves? The answer may lie beneath our feet. One of the most promising strategies for radiation protection is to build habitats underground or within thick layers of Martian soil, also known as regolith. Martian regolith is rich in silicates and iron oxides, materials that can absorb or deflect harmful radiation. Early missions might send robotic systems ahead to construct habitats using 3D printing technology and local materials. These structures would be buried beneath several meters of compacted regolith, providing a natural shield from solar flares and galactic cosmic rays, GCRs. This not only reduces the need for Earth-supplied materials, but also offers greater protection than lightweight surface domes. NASA has already experimented with 3D printing structures on Earth using lunar and Martian soil simulants. These tests show that automated systems could feasibly print walls, shelters, and radiation vaults in preparation for future crewed missions. Another threat comes from solar storms, also known as coronal mass ejections, CME. These sudden outbursts of high-energy particles from the Sun can flood Mars with lethal radiation in a matter of hours. On Earth, satellites like SOHO and SDO give us advance warning of CMEs. Similar early warning systems would be essential for Martian settlers. Colonists would need to retreat to specially designed storm shelters or radiation bunkers during these events, much like tornado shelters on Earth, but far more critical. These bunkers would be reinforced with extra shielding and placed at strategic points throughout the colony, allowing quick access from work zones, greenhouses, and living quarters. Over time, data from these storms would help refine protocols, shielding materials, and warning systems. Beyond passive shielding, active solutions are being researched as well. These include electromagnetic fields that could mimic Earth's magnetosphere, or water jackets that absorb radiation. Water, being hydrogen-rich, is an excellent radiation shield. Tanks of water or even food and waste systems could be placed along habitat walls to add protection. There are even speculative ideas involving superconducting magnetic coils or plasma shields to deflect incoming particles. While these are still experimental, the drive to innovate in this area could lead to breakthroughs applicable both on Mars and for deep space missions. At the personal level, future Mars suits may incorporate radiation-dampening fabrics or wearable shields. Wearable dosimeters would track each astronaut's exposure, allowing mission control to regulate time spent outside and limit long-term risks. Despite the dangers, colonization is still possible. It's about mitigating, not eliminating, the threat. Just as airline pilots are exposed to more radiation at high altitudes, astronauts will need to balance mission objectives with exposure limits. Rotation schedules, habitat design, and smart planning will make it manageable. Importantly, Mars' low gravity, around 38% of Earth's, also plays into this equation. Over extended periods, reduced gravity affects bone density, muscle mass, and cardiovascular health. These factors, combined with radiation risks, create a complex challenge for human physiology. That's why the first Martian settlers will be some of the most physically and mentally resilient individuals ever selected for space travel. Their experiences will form the foundation of future safety protocols, architectural standards, and even Martian medical science. Infinity Beyond believes that with every problem comes an opportunity for innovation. The radiation threat, while serious, is not a showstopper. It's a technological hurdle, one that pushes us to think creatively, design smarter, and expand our knowledge of physics, materials, science, and human biology. Think of it this way. Our ancestors once feared crossing oceans. Now we build ships that can survive tsunamis. Space is simply the next frontier, and Mars is our proving ground. In a way, the radiation on Mars reminds us of our fragility, but it also highlights our incredible adaptability. With every shield we build, every warning system we design, and every structure we reinforce, we declare something powerful, that even in the harshest environments, life finds a way.